Tonight's going to be on battery with VRLA and flooded lead acid. The documents I'm going to use are NETA, and then I've got a document that I've put together for a training class. I'll send that out to everybody. It's pretty in-depth, so we'll skim across some things, go through some basic things that we're looking at and testing. And the document that I have goes over testing with the Albert cell quarter, getting good readings, how you test, how you set up the cell quarter. And then the second half of that document actually goes through the BAS software, which is the Albert battery analysis software. You guys can look at that. It'll show you how to set up a report, how to change your thresholds, change your graphs, whatever you need to do. And we can cover that again a little bit later as well. But we don't want to go over our 30 minutes. So I'm gonna start doing this. Hopefully everybody's at a computer if they can be. If not, like I said, I'm using the NETA ATS, and then I'm going to go over this document that I'll send out afterwards. So if we test electrical test measurements through all voltage connections with the low resistance ohm meter. We're going to measure charger float in equalized voltage levels and adjust to the battery manufacturer's recommended settings. We're going to verify all charger functions and alarms. We're going to measure each cell voltage and total battery voltage with the charger energized and in float mode. We're going to measure inner cell connection resistances. We're going to perform an internal ohmic measurement, perform a load test in accordance with the manufacturer's published data, and then measure the battery system voltage from positive to ground and negative to ground. So that's what NETA tells us we need to do. Western owns one Albert CRT 400. The 400 it's doing an ohmic measurement, but it's looking at internal resistance of the battery. Contrary to popular belief, you don't go in and test with a cell quarter and get all the information you want about a battery, especially valve regulated. You're sealed, you can't get specific gravity, you're not liquid levels. So basically all you're looking at is voltage and then internal resistance. That gives you the health of that battery. A few years back, the state of health for a battery, and what that was doing is looking at multiple pieces of that pie. It's looking at the capacity of the battery. So the way we determine that is, that's the ability to store energy. And when we run a test for that, that's when we're doing a discharge test. We want to sit there, the manufacturer has stated, you put this amount of current on this jar, it will run for X amount of time and will not drop below this voltage. And they have different tables. They have constant current tables. They have constant power tables. So it can either be in battery kW or it can be in ampacity. And what you're looking for is they have a chart that typically will run, most of them have come out in table format, and what they'll look at is 5 minutes, 10 minutes, 20 minutes, so on and so forth. And then they'll have a different end voltage. So it might be 1.67 volts per cell, might be 1.75. And honestly, it doesn't matter as long as you're following what their data shows. As long as you don't dip below that in that time frame, then that piece of the pie is good to go for that jar. You're looking at internal resistance. That's the capability to deliver current. So as batteries age and as the chemical process takes place, you get basically a sulfite that attaches to them and creates a higher resistance. Everyone here, at least most everyone here, has probably heard of thermal runaway. That's when you have so much resistance in that jar that all you're getting is heat and more heat and more heat. And eventually you'll get a jar that can reverse polarity. They can catch on fire. They've actually had data centers have massive damage due to batteries not being maintained properly and having stuff going to thermal runaway. And then the last part you have is self-discharge. So what that's doing is has to do with the mechanical integrity and stress-related conditions. So self-discharge could be your charge is set too low. You have some kind of drain on that battery system, whether it be an improper ground, a path to ground. You could have leakage, thrusters, post seals, all that stuff, and that can carry voltage down to ground, and you've got a lesser state of charge for that battery, and that actually wreaks havoc on the batteries. So can everybody see my screen? Everyone that's looking on,
I got
on the web here?
Yep.
Okay. This is the agenda. Everyone that's seen the CRT 400, this is gonna, if you have seen it, you're probably familiar with it. My guess is you've seen it very little, and it's, you know, once every job or once every 10 jobs. We want to understand the basic functions of the cell quarter, how to set up a site in a cell quarter, which honestly rarely use because we're not going back to the same stuff over and over again. That's typically for a maintenance crew that's going in and hitting the same exact places over and over and over again. The cell quarter settings and menu items, and then taking readings, float voltage, internal resistance, and data storage. So I'm going to whip through the familiarization with the cell quarter because unless you have it in front of you, it doesn't help. Like I said, I'll send this out, and it'll give you a really good idea of how to set up the cell, all of that. So really quick, going through, it's got an LCD panel with what looks like a standard telephone keypad down below. It's got 4 different function keys. They have multiple uses depending on which screens you are, which menu you're in. Up here, you've got 4 LEDs that will show when it's under test, when the USB memory stick is being utilized, what the state of charge of the cell quarter is, and then whether or not you're plugged into AC power. I'm going to hit this 4 or 5 times throughout the presentation. Do not ever test batteries with this thing plugged into the charger. It states it in the manual. I've talked to Albert. We've fried Albert before. The newer models are not meant to be plugged in and being charged while you're testing. So quick breakdown here. Like I said, you've got AC power, you've got charge, USB memory, and the testing. Here you have your standard keypad. You've got numerical. It's an alphanumeric keypad, but it's also got little individual quick menu items there. Over here to the right, you've got the power button. You've got a multi-directional and enter key. And then you've got a test key. Kind of what probes you're using. If you're using the clamp-on probes, you have to utilize the cell quarter itself. If you're using the full-length probes that are the combined probes, it's got a test button on the handle. So this is going to go through some of the menu items of what you'll see on the screen. You've got your main start LCD window, date and time LCD window. This is probably one of the biggest things I see when we get cell quarter data is, again, our Albert doesn't get used very often. It goes into complete discharge, loses it, someone goes in and tests, and now we're testing from 1899 is usually where it'll default back to. Makes it really difficult when you're trying to show what dates you actually did the testing. So make sure the first thing you do after you get it charged, go in and reset the date and time. If you open it up and it tells you that there are readings in the temporary storage, you want to save to the USB device. If you know for a fact we don't need that data, then go ahead and delete it. My recommendation is put the USB device in, save it, put the date of today's date, since you have no idea when it was last used, and at least we have an idea of trying to find that data if it goes missing for some reason. You've also got a frequency for line frequency. This becomes important when we travel to places like Poland, Japan, Belize. We'll want to switch that to 50 hertz. It will filter out as much AC ripple as it can while it's doing the test. Right here, you have alarms and threshold windows. You can go in and set voltages on the cell quarter for high and low voltage, high and low cell resistance. So that's the internal. So you can set high and low for intracell resistance, which are whatever your inner cells are that are connecting you, whether they're solid bus or they're cables, whatever the case is, you can set those internal or the inner cell resistances. Again, when we're on site, we're typically doing a site where we don't have really good information on what that inner cell should really be reading at. I usually don't mess with the thresholds right here on the screen. I'll go through and do all my testing. Once I have my data, when I'm in the software, I'll go through and analyze. I'll look for averages over those inner cell resistances, what the internal resistances are. Again, if you were doing a site where you had 20 of the same strings and you had that information, you can go in there. The cell quarter will just beep at you differently and highlight that cell and let you know that there was an issue. You've got a service window, which we don't care about. That has to do with calibration. You've got the mute to where you can turn the sound on and off. I recommend not, and it's got a really high-pitched speaker on it that will allow you to actually hear if the test falters in the middle. If you're using the extended probes, they have LED lights on them that will actually blink erratically and put you into seizure mode if the test has failed or if it's been interrupted for some reason. And then you have the diagnostics window, which again, most likely you will not utilize. Here's the back of the cell quarter with a telco jack. That's for calibration and for them uploading firmware and doing different diagnostics. We will never use that. You've got the 5-volt DC input jack for the charger. You've got a mechanical reset switch underneath the battery pack. If we ever run into an issue where we have to do a hard reboot on it, that's where we do it. You got your lithium-ion battery pack. Again, if the battery wears down during testing, do not use the charger while you're testing cells. Shut it down, stop in the middle if you need to, whatever you got to do to get it charged. My recommendation is, you know, you're testing batteries the next day, get the thing plugged in, let it sit overnight. In here, this is going to tell us the different specs on the Albert. I'm going to skip past this stuff. Again, this is the basic main function menus where you can go in and set everything up. Typically, you're going to get to this main screen that you see right here. You're going to hit F1 for test mode, and that's going to take you into, are we doing a combined test? Are we doing float voltages first, or are we doing internal resistance? One thing I want to point out, and we've had guys at WES that have forgotten this or have never had the chance to use it, so they just, you have to do your float readings first. You take those voltages, you get all of your voltages. If you've got 10 jars, you take every single voltage first, resistance. And the reason is every time you hit that test button, you're applying a certain amount of load onto that individual jar. Since you're in float mode, the charger is going to spike up to try to compensate for that. That's going to get pushed down the string. And as you go, you will literally create a stair step for your voltage readings. So if you started off at, you know, a perfect, you know, 13.5 volts on a 12 volt nominal jar, by the time you get to the end, in the cell quarter will actually stop at 16 volts and say, wait a minute, you have an overvoltage here, there's something wrong. Make sure you understand they're doing online testing, which is with the charger actually up and running, the battery's on the float. You must take your voltage readings first. Then you can move into internal resistance and inner cell resistance. This here, when I send this out, you can go through and read it. It's going to give you every single menu option and what's in there, what you can set up. These are the key ones here where you're going to go into test code. You're going to say, you can say that you have a total number of cells if you want. It'll automatically calculate overall voltage no matter what. And you can load a site template or load previously saved readings. Again, that's rarely going to pertain to us. All right, so I'm going to skip through setting up a site template. And this right here will give you the maximum stuff that you can put into each item. So the location name can be 39 characters, so on and so forth. So here we are with the test lead connection practices. This connection practices. one of the biggest things is being consistent. So if you're looking at a battery and you know you can get onto the actual post for every single jar, then take every single reading on your posts. If you are looking at a VRLA where maybe the intercell cable is blocking you getting to the post, find a spot on that cable that's good. Look, scan all of your jars, look at them. Okay, I can get into right at the lug and I can get a good connection on every single lug. Then I'm going to make all of my tests off of that lug. The reason is every little difference is going to add to that internal resistance reading. So if on one of them you're trying to take it on a bolt head, which is typically stainless steel, that doesn't conduct the same way as a copper strap does or a lead-coated post does, or a tinned post. So you want to make sure you're very consistent with your readings. Again, we don't go back to the sites over and over again and test the exact same strings. So that's a little less. We want consistency in the jars that we are testing. So we want to try to make sure we connect exactly the same way every time. In order to keep this short, I'm going to skip the test lead connection practices, just the summary here. I'm going to go down to the warning where do not attempt to read an internal resistance of an open cell or module while the battery is on the line. So if you suspect something, you go through and you take your voltages, and it's a 12-volt nominal system, and you come across one that's sitting at like 6 volts, don't try to put a load on that battery. You can get internal arcing, you could cause a fire, you could have off-gassing. That's not what we want to do. So as you come in and you start testing your batteries, you've got voltages first. The owlbear does not care on your test leads what's red and what's black, what's positive, what's negative. It does not care. It only sees it as a positive voltage. You can run through much faster, just daisy chaining as you go through and read. So if you go from first jar here at negative, you can leave your negative in place and go to the next negative with your positive lead and get that next jar's voltage. Most of the guys in WES need to practice is being able to follow the power flow of a battery string. We're always going to start with the most positive jar. That's the one with the positive cable going directly to the charger. That's going to be our number one jar. I don't care how they have them numbered. I don't care what they normally do. We test. When you get your voltage testing all done, you've got your spike probes, and then you have a small set of leads if you're going to use the clamp-on probes for wet cells. Those small leads work great, or the bigger leads if it helps you with higher racks or anything like that. It doesn't care for voltage. When we get into the battery resistance testing, that's when your probes have to be polarity on something like this. You have different ways you'd set up. If you're using the probes, which are the long, 3-foot probes, you set them up for combined, and you would go from to positive, and that combined reading is going to be the internal resistance, and computed would be the jar internal resistance and that inner cell. Okay, if you're doing it combined, that means that you're getting everything at once, and it's not going to look to get the inner cell resistance. When you get into your test mode here, it'll show you how to set up. You're going to go through and select your test modes. If you're going to do your resistance, it's going to ask you what the amp hour rating of the battery is, and it asks you by a greater than, less than. It's either greater than 1,000 amp hour or it's less than 1,000 amp hour. So it's pretty hard to mess that up. It's going to ask cell type. So do you have 2, 3, 4, and I think the maximum is 5. It's going to ask you for the nominal voltage. This is important to know because the cell quarter will not operate if you are above or below that nominal voltage. And once you have all that set up, you're ready to test. So here we are with the clamp-ons. We've got a standard battery system here for wet cells looking down on it. Your red is going to be your most positive. The red-black is going to go onto the negative of the jar you're testing, and the black is going to go onto the positive of the next jar. And what that's going to do is your current path is going to be from red to black. You're going to get 2 different readings there. You're going to get the of the jar itself, all the plates, And then from red black to black, you're going to get the inner cell resistance. So that's going to tell us when you get into bus bars, it's rare to see a failure other than a connection failure. We don't have a tight enough connection, or we've got corrosion in between that inner cell and the post. Those are about the only two things you'll find. If you get into a cable, I've seen cables where the lugs look perfectly fine, the copper's nice and bright on the ends, but we've got corrosion inside that cable that you can't see. And I've actually been there when we tested it, and we had one inner cell that just kept testing wrong. Nothing looked incorrect. The post, we cleaned the terminals, we re-greased, we put it back on, we retested, same result. We finally pulled that inner cell out. We cut the insulation off, and there was corrosion about a third of the way up the cable. And I mean, it was, that turquoise corrosion that was in there was destroying the cable, and it had a high resistance point. So once you get your testing done here, you move on to the next jar, and you have to be careful on the way you move your leads. If you grab your black lead and move it to the, all of a sudden the cell quarter is going to see that you have 24 volts there. If these were 12 volt nominal jars, and it's going to say you have an over voltage, and it's going to beep at you. It's not going to hurt anything, but it's another step to go through and say cancel and clear that out, and then move your other leads. So I always recommend, grab the black and the red leads, lift them completely, set them down, and then move the red and black clamp. And I know we're going through this fast, guys. I'm open for any questions you guys might have when we're done with this. So here is where we're measuring the cell plus the inner cell resistance, the positive. We're skipping that negative post, and we are putting current through the positive, up through the negative, over to the next positive. We're reading it, considered a compute. It's basically internal resistance, or the internal resistance versus the inner cell resistance. These are the two differences between compute. This is how you're going to perform a resistance test, going onto your positive and either going onto your negative or the next positive. In reality, when we're doing the ATS testing, one of the things they want to see is that inner cell resistance. So if we can use the clamps, that gives us the best readings we can get. We don't always have that option, but if we can, it gets us the best read value, even though that is considered acceptable. The clamps are the best way to go. So you get all done. You've got all your readings in the cell quarter. Get your USB device in there. Name it whatever you want. Is going to trigger your head of which one it is. And then in the USB device, put it into your computer and your computer. That way, you've got it on your computer. We're double covered and far less likely to lose anything. So from here down, I'm not going to go over any of this. This is the battery analysis software. I took a lot of time putting together every single menu item, what the toolbar functions are, how you can put comments into the reports. You can do two different read dates. So say we test these 3 months ago, we can set an internal resistance or inner cell resistance. It goes through all the different file types. Everything is in here. So this is stuff that, when you have battery testing coming up, don't wait till the night before. Review this, a couple of weeks before, and then review it again in chunks as you're doing the testing, and it'll help you get through it. Give you an idea. This is what it will look like, depending on what data you have. You've got everything in here from voltage, specific gravity, inner cell resistance, temperature, and internal resistance. And you can make the graph do whatever you want. You can set thresholds. You can set the scale of the graph. Obviously, if you zoom way in a graph, all of a sudden 1/10 of a volt makes a huge difference in that graph. So a lot of times it's nice to kind of scale that back and make it look like a nice even line, because really you're then 100th of a volt or 500ths of a volt, whatever the case is. All right, it is 7:55. Bring on the questions. If anybody's still there.
Hey, Jason, it's Zach.
Hey, Zach.
So the main difference between this and say like a Biddlebyte is really just that software. You know, you still get the impedance, the intercell impedance,
Well,
but then you also
yeah,
get
the big difference.
Go ahead.
The big difference with the Albert versus the Midtronics, the Biddlebyte, most of the other handheld type battery testers is the Albert is actually putting a load on the battery and looking at internal resistance. And you can look at multiple white papers from IEEE. Albert has a lot of them. They always go to BatCon, and obviously they're presenting their product as the best one. But I've used side by side the Midtronics, which does the impedance and is looking at that ohmic value versus the internal resistance. And I found bad batteries with the Albert that we did not find with the Midtronics. And we did a 3-month-long side-by-side comparison of every string we tested. And that's all we did at the time was test batteries. So it's a difference in the way the test is being performed and looking at, putting an actual load on the battery.
Got it. Thank you very much.
But the testing is very, very similar. You're performing the same. You're basically doing the same types of tests. It's just what are they using to get their results.
Yeah, this is it. Hey, Jason, good presentation. This is Anthony. I had a quick question. I wrote down, I'm trying to take notes while you're going through this, and it's kind of quick, but the one thing that I had written down was you were talking about these batteries that are daisy chained together, and we're moving the leads from positive to positive. Is it typical to see more than just 2 batteries daisy chained together?
Yeah, if you get into the and even in station batteries and everything else, you have it's rare that you'll see jars paralleled together. It does happen for capacity. What you'll see are strings paralleled together. So if you walk into a data center and you see a UPS, you'll see a string of typically 40 jars. They're 12-volt nominal jars. Their float voltage, they're usually sitting between 540 and 545 volts per string. And a lot of the UPSs actually have the capability of operating with up to 6 strings. So you'll have 6 strings in parallel.
Okay, so when you're doing these tests, these resistance tests, you're moving one positive to the next battery, and then you just move like moving one at a time over to get those resistance checks. You're not trying to keep one at the first and then just can progressively move down because you'll trip it over that over voltage that you're talking about.
Correct. You'll do individual jars. So when I talk about so the industry standard when we talk about batteries is a battery, the entire string. 40 jars because if you take a jar, container is, so there are jars out there that have 2 cells. There are jars out there that have 6 2-volt cells. So that jar is basically whatever the container is that contains that group of jars. In order to change that one cell out, you may have to take out that jar which has 2 cells in it or 6 cells in it. And I know this being a nuke, like a car battery has 6 cells in it, right? When we're talking about lead acid, it's always a 2-volt nominal for every cell.
Okay, that makes sense. I got it. Thanks.
Okay. Anybody else have any questions? I went through it pretty quick, and I'm skipping lots of data. One thing I do want to go over really quick is when we're testing batteries in that state of health, the data center, when we go in and we're commissioning Mexico, if they were asking us to test batteries, they're looking for what is the initial state of the battery. So they want us to go in. We're going to do these tests with the Albert cell quarter. They're going to see that, okay, all the voltages were good, internal resistances were good. We're going to make sure that we're doing whatever the manufacturer, if we're going to do an equalized charge or whatever they call for, we're going to do that for 72 hours or whatever the manufacturer asks. Then we're going to move into doing our capacity, right? So we're going to do our charge test, and with all of those different results combined, they can know for sure that starting off at as close to 100% of capacity and as it can be. So they're looking for warranty defects. They're looking for a jar that drops off too quickly during the capacity testing, and they want to make sure that good health and injuries that are they're a 10-year design life, and in all honesty, the most you'll see out in the field is 3 to 5 years. 10-year design life means that you're at exactly 77 degrees. Your charger has 0 AC ripple going through it, and the battery never takes to discharge. And the UPS never operated, or the station battery never had to feed power to any of the control system. So basically, in a perfect world, if you put that battery in a climate control room and it got touched, then you might get 10 years of it. And I've never seen, when you get into the wet cells, they're typically a 20 to 25-year design life. And really what they're seeing is somewhere between sometimes 10 to 15, and I've seen them go out in 7 to 8. So they go through and we do this initial testing, we're giving them the documentation. Now either they're on-site guys, they're facility guys, or they're bringing in a third-party vendor. They're going to come in and test those quarterly or, semi-annually, whatever their testing plan is, and they're going to look at the data, and they're going to start trending jars. And the second they see, this is the good places, the second they start to see an internal resistance rise or a capacity dish fall off early, they need to be replacing that jar and getting it out of there and trying to keep the health of the string going. That string is basically a living organism, bad jar or one bad cell in it affecting its neighbors. So if you've got one with high resistance, it's going to take less of a charge. Well, now its neighboring cells and its neighboring jars, the voltages start to go up. Now you're overcharging the battery and it starts affecting it and going outward from that first initial cell. So realistically, when it comes to batteries, we, in acceptance testing, we're looking for a manufacturing flaw. We're looking for some issue with that jar that they need to get warrantied out right away. If we're doing maintenance testing, then we're looking at, okay, do we have any data that they've collected over the years? Here's where it sits right now, and all we can do is a best guess off of the manufacturer data if we don't have all of that previous data. So if they've been in there 3 years and we go in and test, we're making an educated either based off of the knowledge we have on those jars and how they perform. We're doing it off of their previous data that they have, or we're taking a shot in the dark and saying, okay, right now the entire string together looks like they're all about equal. We'll run a capacity charge or a capacity dish, and we'll compare specs, and we can tell them whether they're in good or bad shape. But we're not going to sit there and tell them, what, you've got 3 months left on these jars and then they're going to fail. It's predictive analysis is what we're really looking for.
Hey, Jason, this is Matt.
And Matt, I know you were on here. I knew you were going to want to say something.
No, I just great
He
job.
loves batteries.
Whatever. So, the only thing that I would like to add, and you did a lot of great information. The one thing that I see when I'm out in the field all the time is a sense of DC is safer, or there's a lack of the respect that it needs. That simply cannot be further from the truth. So there's a whole list of different PPE that is required when we're doing a lot of this testing. We do have a DC safety test kit that's got a bunch of additional PPE that we normally don't have. For example, aprons, face shields, that kind of stuff. But just keep that in mind. There's a ton of safety If you ever get hit by DC, you'll understand the criticality of why you need to be safe around it. And so take a look at that. It's also a lot of questions on the NETA exam, just the PPE and the special requirements for safety as you when you're working around DC voltage.
And I'll add on to that. Speaking as a person who's been hit by rectified AC, it hurts. I got hit with 540 years and years ago. I know I'm not. It is, DC doesn't let go. And even more, everybody I've ever met has jump started a car at one point, taken the two ends of their cables and they touch them together and there's a little spark, right? If you do that with one of these UPS batteries or a station battery, it's going to weld those clamps together. It's going to blind you. You're going to have dirt everywhere. It is a different plate design, and it is designed to dump its current as fast as it can and as much as it can to be able to support that UPS. And it's instantaneous. And yeah, to go off of what Matt's talking about, you have all sorts of different dangers when it comes to batteries. You've got acid. I'm still torn on whether I would ever put an apron on doing specific gravity or anything like that, because I know that they've started coming out with FR safe aprons, but it's really hard to have acid proof and fireproof. The two just don't go hand in hand. So it's something to be really careful with. If you're ever interested in to see the competition between AC and DC, you can get on YouTube and you can go look up some different tests with elephants. All right, anybody else have anything? Joey, I know you have a comment.
No, the only question that I have is obviously I know your experience, Jason. So are we actually starting to do more battery jobs, and with that, are we actually going to move into the field of jar replacement and the old Swedish medical, or are we still looking at calling your old company and saying, hey, you guys are the professionals, you do this?
If I have it my way, I would resist having us do battery work. Doing the testing of station batteries and stuff like that, not a big deal. Doing the replacement work, it takes a different set of tools. It takes a different mindset. It takes a different back strength. It's just one of those things. And there's a lot of competition in that realm. For us to go in and try to compete with guys that are buying batteries nonstop, and there are groups of companies that have gotten out there and put main power together. It's just hard to compete with. I would much rather sell the job, farm it out, and we'll make some points on it and let somebody else and go that route. Now, Matt can probably speak to that. I've never heard anybody start talking about wanting to get in the replacement world.
No, you're absolutely right, Jason. That's something that we try to steer away from, bring the system matter experts in. That's not to say that we won't. We have done it on smaller control power systems, but those are one-offs, and we try and stay away from them as much as possible.
Yeah, this is more for, most of the time, if we're out doing testing, we've got this Japan job coming up, and we've got 2 battery banks that we've got to go through and do testing on. They come up every so often, especially when we're getting into more of these projects where we're doing complete one-off systems like Japan and Poland. I know that we've done them in the past out at what was it? One of the combined cycle plants out there in the Columbia River Gorge. Joey, I think you were out there. And we did, I think, 6 or 7 really large wet cell systems. And so it's just something we don't get to do it to be good at it. So I'd rather get more and more training on it so that when we do come up against it, we're prepared.
Hey, real quick, Jason, Anthony had a question. I want to make sure we get caught before everybody jumps off here. He's asking about when we're doing the testing, and in particular, one guy working, he wants to know if we need a rope guy for additional safety to pull off.
Well, I can say this, that I've never seen anything in NFPA that called for a rope guy. Typically, if we're using the right safety precautions, I don't see a need for it. Most of the companies out there that are doing battery testing, it's a single guy going in and testing with an Albert or similar device. When we get into the capacity testing, when we're making our connections and everything, it's got to be I would have two guys there and walking through, making sure that we're connecting appropriately, and running the test appropriately, and making sure we're following the manufacturer's guidelines.
Okay, yeah, I appreciate it. Like every being on a submarine, like a lot of stuff is DC, and every time we've done DC work in the nuke field, the guys always roped off face shield, apron, those gloves, and everything like that. So that's kind of typically what I'm used to seeing.
Yeah, and so one of the have, in the sub world, you guys are working on pretty big battery systems, very large jars. When you get into, and this is still something that the NFPA has wrestled with for years, you get in front of a UPS battery cabinet or a station service battery rack, you can't go through and torque and take most of the readings in a 40 cal suit. And so it's one of those things where they've kind of stayed away from it on the arc flash side. I know that is changing, and it's changing rapidly. That's why you're seeing battery monitor companies going crazy. There used to be a couple of them out there, Albert being one and CellWatch being another. Now they've got 50 different battery monitoring systems out there. Those get permanently, well, not permanently, but they're attached to that jar for life. And they're relying more on that for all of their battery analysis, with the exception of going in and torquing. And so torquing, you do need to suit up to whatever cal you need to when you're doing torquing. And you've got to use insulated tools. I mean, you get into some of these cabinets and it's extremely tight. Joey's seen some of the UPS cabinets and worked on some of those. It's a different animal. And one thing we will do is we will buy specialty tools and stuff if need be. If we're going to be doing anything like that, we will go the right route and make sure we get the set that we need.
I'm sure, Jason, that you still probably have your slip sleeve for your ratchet that's insulated that we could use.
Yes, I do. I don't know that meets any kind of industry standard, but it has never failed me.
Hey, Jason.
Any other questions?
I got one more quick question. I'll let you go.
Okay.
Would you? I know you kind of slipped over for a second. Would you recommend disconnecting the charger?
No. If you look at, so I'll pull this up here really quick. If you're looking at NETA here, when they're looking at you doing your testing, you'll see it right here. Measure each cell voltage and total battery voltage with charger energized and in float mode.
Okay.
So that is an online test.
Gotcha. Thank you.
Yep. All right. Well, if anybody has any other questions, feel free to email me. I'm going to send this out to the entire group, and they can review it. Keep it in your, everybody's got their special folders on their laptops. This will be one that'll come in handy. You can go back and look at it. Again, I don't know how often everybody sees the owlbear. You'll come across it once a year, and you'll look at it and wonder, how the hell do I set this up? So hopefully this will help. And again, if anybody has questions, I'm available anytime. All right, with that, I'll let Matt conclude the meeting.
No, you're good. I was just saying thanks.
Okay. Thank you, guys.
Thanks, Jason.